Well, thanks for joining this talk. Sorry, the live feed doesn't seem to be working well if we're switching to this, but I'm happy to talk to you today about encapsulated phase change materials as a pathway to enhance thermal capacitance functionality and electronics temperature management. I'm David Huitink. I'm from the University of Arkansas, and this is a key part of some of our materials development and electronics thermal management. And so today, the talk specifically is going to focus on thermally active materials, in particular reference to encapsulated phase change materials. And so we're going to take a look at what that means and the benefits of it and how they've been implemented in some electronics material systems for managing temperature transient spikes. And so really what this gets at is, electronics are thermally limited. This is really the big reason for power limitations in electronics, whether it's from CPUs as well as power electronics that may be used in vehicle systems. But the advances in thermal management often focus on peak power reduction and don't always focus on transient temperature management. And when we talk about EV power systems, like you see in power electronics, there are a lot of transient load events that you can encounter. You can imagine trying to accelerate away from a stoplight, that there is a sudden burst of energy that has to be dealt with in the electronics. And that power spike leads to a very rapid temperature rise in the electronic devices themselves, which can contribute dramatically to electronic failure. Temperature and temperature cycling are the two dominant reasons for reliability failure in electronics, because of the things that happen with material degradation as well as um, uh, thermomechanically induced fatigue events in electronics. And so being able to control these transient temperature spikes is a very important aspect of the overall thermal management solution. And this is where PCMs or phase change materials have specific opportunity. So a phase change material essentially is something that undergoes a phase transformation, and that phase transformation happens isothermally or essentially isothermally, where you have energy absorption through that phase change that is controlling the local temperature as that energy exchange is taking place. So where you might see a temperature rise that goes above the safe limit without some sort of latent heat incorporation, that incorporation of phase change can delay that event so that you have more time to respond to the thermal event in your system. And this is what this looks like in one previous example of an article that we published on phase change materials integrated into electronics. The incorporation of phase change materials essentially delays the time to which you hit a critical temperature. So let's just say something like 100 degrees C, you almost get a 3x improvement in the time that it takes to reach that temperature by taking advantage of this latent heat capacity associated with phase transformation. And this is really just going down to the basics of melting and solidification thermodynamics, right? This breaking of the bonds and the resolidification is uh, a energetic event that can be endothermic in the melting and exothermic in the solidification. And if we leverage those appropriately within a thermal management system, we can really do a lot to ameliorate the temperature spikes in an electronic system. But the problems with phase change materials are not small. Of course, if you have a transition, the phase change from a solid to liquid, for instance, a liquid can tend to flow. And also and that has to be dealt with. So you can put in some sort of enclosure to try to keep that from happening, but there's also effects of volume expansion that play a role as well. And how do you contain that material reliably? But also with the phase change materials of interest in electronic systems for the melting temperatures that we're interested in, it limits us pretty much to organic phase change materials, which tend to have very low thermal conductivity, which again is a drawback in the thermal management system. You want to have something to have fast or expedient heat removal through a high conductivity system. So these organic materials are not always well suited. And there's also issues with compatibility and reliability, which we'll talk a little bit more as we go forward. But ultimately, all these things come back to this idea of integration challenges. We have these material sets that are available to do latent heat storage or energy absorption through phase change, but we don't have good delivery mechanisms to get them into the materials very easily. And it takes a lot of effort. And that's where we have really been focusing on this idea of encapsulated PCMs. Our ePCMs are essentially a thermally active core consisting of the phase change material surrounded by a non-thermally active shell that contains it and acts as a delivery vehicle for this latent heat storage mechanism. Here's some TE images of what this looks like. And really the novelty of what we've been doing at Arkansas is to deliver submicron size ePCMs that are much smaller than anything that has been produced commercially in the past, but also have some improved properties, as we'll see here in a little bit. And we are producing these here at Arkansas using a sol gel method. So essentially we create an emulsion of the phase change materials and use a sol gel process to encapsulate them with an inorganic shell um, that basically contains them in this small form factor. And so what this allows us to do is really multiple things, right? So we no longer have the issue of leakage because the shell itself contains the EPC or the PCM material so that it cannot escape. But it also, the shell can help to improve the heat transfer performance as well because the shell itself has improved thermal conductivity. But it also is delivering in a small particle also increases the rate of that phase transformation because you have more surface area of engagement with the surrounding temperature environment. And moreover, we can improve the reliability and stability of the PCMs, and our synthesis process allows to tune properties with the different materials that we use. And the choice of materials also can help with electrical isolation and incorporation to other materials. So just a quick note on the leakage prevention. When you have a normal PCM or bulk PCM like paraffin, for instance, as you heat it above the melting point, it melts and it flows and it spreads out, which has to be dealt with. In the case of the ePCMs, it looks like a white powder here. That's just the particles. And above the melting point, we notice that there's no observable morphological change or leakage event, but yet we're still seeing the thermally active event. But we're also seeing that that shell improves the stability of the organic material on the inside. When we do TGA testing, we see a slight delay of the degradation of the interior PCM because we've now basically encased it in the shell, which makes it opportunities for integration in electronic systems even better. So we've talked about electronics cooling already, but there's also opportunities in building construction, solar energy storage, as well as heat transfer fluids for improving the heat capacitance of coolants. So here's a quick look at some of the ePCMs that we've synthesized and published on in the past couple of years. You'll notice here that we have paraffin and MA, which refers to myristic acid, which is a fatty acid. Paraffins and myristic acid have a melting point that are similar, but they are approximately in the 55 degrees C range. And we can encapsulate those with various inorganic materials like silica or titanium. And the cool thing here is that we are able to achieve the latent heat capacity within these ePCMs that are still meaningful. But again, with the shell, we have an area of that particle that is now non-thermally active. So that's what we refer to as encapsulation ratio, because essentially 62% of the mass of that particle is participating in latent heat exchange is what this refers to. And we also see some good things about latent heat retention over a long period of cycling. As we go through 1,000 of melt and resolidification cycles, we notice that we have very little loss in the performance of the materials. And so this is important too for integrating it into a system where you want to have these operating for a long time and maintain stability. And we also see that as we look at the stability of the actual PCMs over time, if we were just to sustain high temperature of paraffin, for instance, over a long period of time, we see a lot of evaporation of that paraffin itself and deterioration, and that would continue indefinitely. However, in the case of the encapsulated versions, we see that there is very minimal mass change in the initial stages, and then it's very stable from there on. So the shell is effectively holding all that together and keeping it from leaving the system. This initial loss that we see has to do with adsorbed water onto the shell that is baked off in those initial period of time. But again, it's very small amounts. So with these benefits right now, then we can look to going to integrate them into systems. And so in power electronic systems, often we use an encapsulating silicone to provide voltage isolation, but that also is at the detriment of thermal performance because essentially it becomes a blanket for those devices. So while it's isolating the voltage, it is also contributing to higher temperature events. And so if we can integrate ePCMs into the silicone gel and maintain the voltage isolation function, but also be able to have thermal capacitance and thermal storage close to the devices itself, this gives us the opportunity for managing those transient temperature spikes. And so what we do is essentially take the ePCM particles that we've synthesized and mix them into a two-part silicone gel at various loadings, and you can see the outcomes of that here. So let's take a look at some of the properties that we see thermally when we add these. Of course, the primary metric is, do we add latent heat capacity into the silicone composite that we've created? And the answer, of course, is yes, right? As we add more ePCMs into the system, we see an increase in the total latent heat capacity of the system. We also see a slight increase in the specific heat. So essentially, this also helps with the sensible heat or sensible temperature rise when heat is being generated from the devices. So we see a combined effect of benefit from sensible and latent heat effects. But the other side of the equation too is how does this affect the thermomechanical aspects of the system? When we think about electronics, often thermomechanical issues are top of the line in concerns about reliability because of the thermally induced cycling fatigue that can take place. And these silicone gels are used often because they're very soft, and so they don't impart much stress onto that, even though they have a high CTE, because it's really a combination of both the stiffness and the CTE, or thermal expansion coefficient, in doing this. So because the ePCM particles do expand through that melt cycle, they do exhibit a significant increase in the CTE for the materials. However, the stiffness part, since we're having a relatively minor addition of particles in terms of the loading percentage, we don't see a big change in the stiffness of the materials. So the net effect is that we get to see, we do see some impacts to the overall thermal stresses on the system, but we are doing that. That's the detriment to getting the thermal benefit as well, which consequently, if we can control the temperatures a little better, that helps us even to counteract some of those effects. But of course, as I mentioned, the high voltage isolation is the big name of the game here. These systems are often operating above 1 kV. And so you have to be able to prevent discharge or any sort of leakage event through the silicone encapsulation, encapsulant, I should say, not to be confused with encapsulation of our particles. But incorporation of particles into the silicone does result in reducing the breakdown voltage associated with those gels. However, even though we see about a 50% decrease in that breakdown voltage, the good news is that we're still seeing that this breakdown voltage exceeds that of air. So we're still seeing a benefit relative to no encapsulation whatsoever. And so this really kind of points to some of the trade-offs that we see in the properties. We do see an improvement in the thermal storage, energy storage here in the green bars. But that comes along with some of these stress effects, as well as some of these voltage reduction effects. So it really comes down to tuning the mixture of the composites to accommodate the multiple requirements, electrothermal and mechanical aspects in electronic assemblies. A second area that I wanted to touch on briefly, as far as another application, is thermal interface materials, or TIMs. These are used at interfaces of essentially devices and heat removal technologies. So it could be a heat sink or a cold plate. And they exist to reduce the thermal contact resistance between the two surfaces. So typically these are greases or gels that have low viscosity that can fit into small asperities in the surface. and their main function is to provide a conduction pathway to the heat sink. But this also provides opportunity of integrating these ePCM materials for adding thermal capacitance locally near the heat generating area so that we can smooth out any transient temperature spikes on the device as well. So we looked at three different materials, TIM materials, and added these ePCMs into the system to look at the thermal capacitance addition that we can achieve. And of course, like we saw in the silicone gel, the increase of particles is proportionally affects the latent heat capacity of the materials. And we also see impacts in terms of the specific heat capacity that we can see the overall thermal capacitance of the system through adding ePCMs into the composite mixture. But again, this can't be viewed in isolation because there are other effects in terms of thermal conductivity of the material and its contact resistance. We do see a reduction in thermal conductivity with addition of particles, and this largely has to do with the percolation network of thermal pathways through the TIM. The TIMs themselves include particle loadings that are high conductivity to try to improve this. So by integrating into that network, we're actually reducing some of that network, and it does follow classical models quite well. But we also can see that as we add more particles into the system, we do see more contact resistance arising too, because essentially we're creating a new material interface that is not well tuned for the system. And so there's a lot more work that can be done here for tuning this, but it is material dependent in terms of what is the medium by which they're mixed in. And so differing effects depend on those chemistries. But one thing that we can do is we can look at incorporating other particles as well, which allow us to improve those thermal conductivity effects. So we looked at incorporating carbon nanotubes to effectively raise the overall thermal conductance or counteract the loss that we see from the ePCM particles. So essentially this becomes a balancing act of, of the loading of ePCM particles, which increase our thermal energy storage in combination with increasing the thermal conductivity coming from the carbon nanotube. So there are some sweet spots that can be found in that optimization. So just as a quick overview here, of course, we're just introducing this idea of encapsulated phase change materials just to bring to attention the opportunities that we have with integrating thermal energy storage directly into the materials that are used in electronic assembly. So TIMs and silicone encapsulation gels in this case were discussed, but there's a lot more opportunities because the ePCMs offer a reliable and robust approach to good integration of thermal storage into material systems such as electronics. So with that, I'll wrap up there, but acknowledge funding from POETS, AFRL, as well as University of Arkansas. Thanks for your attention and happy to discuss with you more.